Welcome to the SEI podcast series, a production of Carnegie Mellon University's Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the United States Department of Defense and operated by Carnegie Mellon University. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts. My name is Will Hayes, and I'm a principal engineer here at the SEI. Today I'm pleased to introduce you to Dr. Peter Feiler, technical lead and author of the Architecture Analysis and Design Language, more commonly known as AADL. Dr. Feiler will be the second researcher featured in our SEI Fellow series. These researchers are so named because of their outstanding contribution to the work of the SEI and from whom the SEI leadership may expect valuable advice for continued success in the Institute's mission. He has lent his expertise in this area to several recent Department of Defense projects, including the Army-led Future Vertical Lift program, which will bring in the next generation of military helicopters. Today we are going to talk with Peter, who was named an SEI Fellow in August of 2016, about his career, his work on AADL, and his thoughts on the future of software engineering, and more importantly, securing safety-critical systems. Welcome, Peter.
Thanks for having me.
So it's not often that we get to speak with someone who can bear witness on the evolution of software engineering as a discipline and who can legitimately be credited with a substantial contribution in a new field, particularly in model-based engineering. I like to think of advances in programming languages as providing more structure and more help to the people who create products that eventually get converted to zeros and ones. But the work that you've done has far surpassed the complexity and aid that compilers provide. The modeling language you've developed and the work you've focused on in your career has really helped to assure performance and correctness of software in very profound ways. So where do we start?
Well, first of all, thanks for the compliment. But yeah, I will go quite a bit back, and one reason is because all of those pieces in my history played together and came together when I had to do the work in AADL. I started studying in Munich in 1971, and two of the professors I studied under was Professor Baumann and Bauer. Both of them were involved in coming up with ALGOL as a language, and the first language I learned how to program was ALGOL 68, which was a relatively high-level language at that point. In 1974, I then had a one-year scholarship, which led me to Carnegie Mellon. And that's where I came across Nico Habermann, who became my advisor. And his history is interesting, too, because he got his PhD under Dijkstra. At that time, they were doing the THE operating system, which pursued the concept of virtual machine layering. Nico then crossed paths with Parnas at CMU in 1967, and that's where both of them got the idea on how to combine the module concept with machine layering concept. So when I got to Carnegie Mellon, Nico was doing this project called Family of Operating Systems, where we architected an operating system in such a way where we combined those two concepts. Later on, I then took this concept and brought it to the CM Star project, which is a multiprocessor project led by Anita Jones. So while Nico Habermann was on sabbatical, I continued with that work. On the side, Nico Habermann's thesis work itself was on the use of semaphores and how to avoid deadlock. And that was actually one of my interests, was dealing with concurrency and all that. So I continued working with Nico on the side on that topic and notions of past expressions and that kind of stuff. During my time at CMU, I also took a seminar with Mary Shaw on language design. And I finally did my thesis work on something called Gandalf, which is generation of software development environments from formal specification of languages.
So if you could speak in perhaps layperson's terms about what Gandalf did, because I've heard a little bit about the background on this, and it seems a novel introduction of concepts at that time.
Yeah, at that time, what happened is people traditionally were writing code as in a text file and then handed it to the compiler and then it ran. What we said is, let's create an environment where you interactively are doing these things and the system knows the language and it acts as if it was interpreting the code, so at any point in time we were totally up to date. Today we are familiar with those kinds of environments. The first one that was pursuing that idea commercially was actually Rational with their Ada environment. Later on, you find it nowadays with a lot of environments. And but this was in 1979. And the way we approached it is to say, can we do that work by actually generating it? It's like parser generator, just generalized to generating complete environments. And again, those concepts you can find today in tool environments like Eclipse. There's the Eclipse modeling framework. And now this X-text generation environment, technologies that we use to implement AADL.
And people take this for granted.
Today they take it for granted. We did that as thesis work, so I could reach back to what I did for my thesis work when I had to implement the AADL standard. So that's kind of why I'm telling you the history. A number of those pieces all are relevant to the kind of issues we are trying to address with the AADL language. Yeah, and so when I was done with that, I went to Siemens. You have that listed. We started the research group in the software research group in Princeton at the corporate lab there. And during that time, I also had a chance to spend a year out in Oregon, where we had 200 Siemens people doing work with 200 Intel people on a new processor architecture that became the i960 processor. And then when the SEI opened up in '85, I came back to the SEI, ran across people like Mary Shaw again, did some studies on user interface, got into configuration management, environment work, became a program manager, did that for 6 years. After I stepped back from that, I got involved in some of the work Louis Shaw was doing with Simplex, and Bruce Lewis then got me involved in the AADL work. So I have been working with Bruce since 1997 under his funding to turn some research work into the standard and moving forward where we are today.
The sophistication, the process of growing more and more sophisticated in the way we manage the production of that long string of zeros and ones, that really the formalization of that is really where your career is focused.
Yeah, and always has been. I've always lived in notations that have strong semantics, strong typing, that as early as possible we can identify issues that you may have in your system, because that's where, I mean, you want to catch things when you introduce them, not have, I mean, you don't want to drive a car and find out when you go down a steep hill that your brake doesn't work.
So in looking at the influence of this kind of work on the products and services we've come to take for granted today, the level of discipline and foundational work that underlies the techniques in use today, I think most folks don't really realize how much careful work went into it. And you're one of the people who was there making it happen from the outset.
Well, and taking advantage of other work that has happened, because some of that stuff, for example, came out of Xerox PARC. Being at CMU, I was already working on machines that today are known as Macs and things with mice. In 1976, I already worked on machines with bitmap displays, menus, and mice and stuff like that. So I have had very early exposure to some of those technologies, which then helped me pull a lot of that stuff together when we worked on the ADL standard. So it wasn't just language design, but everything else around it, and taking it from a programming language level. Like Ada was very good for safety critical systems because of it having strong typing and all that. We took over all those principles and just moved it into the architecture level as well. And at the same time, the importance of architecture has been pushed by the SEI through some of the other work in our architecture group as well.
So just as strong typing influenced programming languages to be more reliable, more secure, the concept of typing applied in an architectural sense seems to be where AADL is going.
That is one element to make sure that what you specify in this notation is consistent and fits together. The other element of it is what we wanted to do is put in semantics into the things that you express in AADL that are close to what we are interested in, namely embedded software. Software by itself doesn't do anything. You can talk about the function of software, but if you want to talk, say, performance, you only can talk about that in the context of it running on some hardware. if you want to talk about safety, you have to talk about how it runs on the hardware, how good the hardware is in addition to how good the software is, and how well it interacts with the physical environment that it deals with. And because that's where the problems are. And this is what industry studies had shown, that for software systems that are called embedded systems or fiber physical systems, people call it today, 70% of the problems are introduced during requirements and early architecture specification, and 80% of them are not discovered until post-unit test. It clearly indicates we know how to write the functions, but it's the playing together that matters, and that's where we didn't have good tools. And that's what this notation focuses on, is can we define that part of it so that we virtually can integrate the system and virtually already determine these pieces will play together.
So rather than having to wait for the hardware interaction to occur and observe it when it's already been encoded, the abstractions that are available to you allow you to simulate and to really compile and test and run the model prior to that time.
Yeah, exactly. And like early, what happened is they had an aircraft sitting there. They had a software build, they put the build on, nothing happened. Okay, so there were some configuration issues in the build, so then it fixed those. And then the first time they started up the aircraft with the software, then the screen started going blurry. They had no idea why it was blurry. It's things like that. So the thing was still sitting on the ground, so we hadn't even flown yet. Mm-hmm. And then it just continues that way. So it was kind of you kind of explore the thing, and we want to engineer these things. And that's what made it hard, is as we moved forward and put more and more software into these systems, so they were not in isolated pockets anymore, but you cannot drive a car anymore without the software running. You cannot watch TV anymore without the software running. You can't even use a refrigerator anymore without software running.
And with the Internet of Things, all of those devices you just mentioned speak to each other as well.
Exactly.
With the software running.
Yeah, so I mean that's what we are facing nowadays, and that's why this whole issue of safety and security are just so important. And if we do things right, we actually can save lives that way. So even though I'm not being a doctor, I can save lives now.
Okay, Dr. Feiler. Well, so what are the new frontiers? Where are you pushing it now?
Well, we have come from the safety side, because that's the domain we have come from. Mm-hmm. But both with us within the group and being at the SEI, security has come into the picture, and also the research community has done that. There's a DARPA program called HACMS, where they're interested in making these autonomous vehicles secure. And one of the teams is Rockwell Collins, that have been always very strong in model checking type of thing. Rockwell Collins, about 8 years ago, then embraced combining model checking with AADL to get the scalability. And so we have been working with them together. So they brought that technology that had its roots in safety and applied it to security. When they did that on a UAV, after 18 months, they then gave that system to Draper Labs. They had a red team trying to break in from a security perspective, had access to the source code. And in 6 weeks, they were unable to break into it from a security perspective.
So is it like saying not only are we modeling the behavior of the hardware, we're now starting to model the behavior of humans interacting with the system?
And the software and the assumptions that are being made, because most of the security issues are low-hanging fruit holes. The sophisticated ones, people don't even have to bother yet. I mean, buffer overflow type of things are the easy ones that people kind of break in today. Those are the ones that were closed up by the work that these guys were doing. There's some behavior interaction where I can get you to be out of sync with me. You think I'm doing this, but in reality I'm doing that. They have started addressing that as well, and then the next layer will be by playing around with time. I can get you confused by pretending like I'm at a different time and so on. So people haven't had to use those kinds of issues yet. But we see those problems currently from a safety perspective. And there's plenty of examples that we can point to where software has caused accidents because of those kinds of things.
So clearly this field is continuing to grow. What do you see as the major milestones coming?
Well, going forward, there is On the security side, the approach has been, let's build a firewall and protect us from the outside world. And for those of you who know Alder Guthrie, he has this shanty thing where he says we can't build a fort all around America. We cannot protect ourselves from the outside world. We need to make sure that we are resilient and robust inside, whether it is from a security perspective, breaking in externally, or from a safety perspective, because we never can write zero defect software. So even unintentional issues still have to be faced. So what we need to do is make sure that there's robust kernels that are verified, on top of it firewall type of mechanisms, so that just because I'm able to break into your entertainment system on your car, I cannot send commands to the autopilot and to the brake system. Those need to be isolated. They need to have authorization to do that kind of stuff. And it's those principles that just need to be pushed through. For a long time, people were arguing in embedded systems, we don't have the cycles to do that. But even for your desktop spends 80% of its time virus checking and doing stuff like that, which we wouldn't have to do if you would have strong hardware support for that kind of protection in there. So I think on that front is one area where we can make some progress, and technology that is a combination of what we do on the hardware side and what we do on the software side.
So an allocation of those concerns to a different layer of the architecture as a structural influence on the industry as a whole.
And also shifting it to say, we cannot guarantee things up front, therefore we need to put some sanity checks inside, so you do continuous monitoring, which is stuff that we do on the security side. They monitor the traffic, but then also put from the beginning protection mechanisms in place so that we can get better isolation.
So instead of virus checking being an application that's installed, virus checking is a presumption that exists in the system when it's first built.
And also that once you get into a certain area of your system, you are then limited to what you can do at that point. Because once I'm inside your PC, I can do anything I want. Okay, that shouldn't be the case. If I'm in from one window, like an app type of interface, then all I should be able to do is access certain things. But that requires enforcement of those things at a granularity that currently we are too coarse-grained.
And so the modeling approach, the modeling approach that would evolve from what you're talking about would force those concerns to be addressed prior to anything being built.
Yeah. Well, it's like when we go and say, from a safety perspective, and this is, by the way, also a complaint that Nancy Levison has about people that do hazard analysis. She says, people focus on parts failing, and then how do you deal with that as a hazard? But you can have a system where both parts are fully functional, but the way they interact with each other creates a hazardous state. Okay, and so what you have, one way of looking at it is you just have to go up one level and look at whoever put those two things together. It was their responsibility to understand what those interactions are and what assumptions one side made on the other. Where in some cases you may not have control over one side, like if it's a train and a platform, you don't have a control over the platform, but you have control over whether the train stops at a platform or before the platform, before you open the door. So the train does fine, the platform does fine, but the control system that understands the relationship of the train and the platform may not understand that. And that's where we get these issues. And that's one message that, like Nancy has, where she says, there's a new class of issues that you need to discover, and we are doing a similar thing. We also, in that context, for example, one of the standards in the AADL standard suite focuses on fault modeling, and in that context, we have a taxonomy. And in that taxonomy, what we are saying is, have you thought about, given the subsystem fails, like a break, does it break when it's supposed to, or does it not break? Or would it break at a time when it's not supposed to? So it's omission, commission. It's also, how hard does it break? Does it break in time? Those kinds of things. So there's various parameters that you can go through as a checklist and say, have you considered some of those things? Because that's what we find in many systems. They thought about some, but in the one case, it was for an engine control system, actually getting a command too early caused this thing to misbehave. Most people think only if something comes too late, then things go bad. Well, sometimes things can go bad when things happen too early.
So these would all seem to be important prerequisites to the notion of autonomy.
Yep.
Without these kinds of things being thought of, autonomy isn't achievable.
Well, and then that gets into a whole other game, and that is with autonomy, there you have to have a model of the world that you're living in or that you're trying to be autonomous in, and you now need to make sure that those things fit together, and when you come to some boundary condition that doesn't fit with the understanding of that world, then you need to say, I don't trust this autonomous system that it understands that world. So that's pretty sophisticated stuff that still requires a lot of work. To get to some of that, at least we are taking out some of the layers below. Because like when you build autonomous systems, there's these, the robotics folks have like a 5-layer model for the whole thing. And so once you get to a certain layer where you get into the planning and understanding your environment type of thing, if you can't rely on the lower ones, then that doesn't work. So given we can do that, now we can focus on what we need to do up at this layer. And some of those techniques actually go back to, for example, ideas that Louis Shaw had when he was at the SEI with Simplex. The way he had dealt with software faults is making copies of the software that's faulty doesn't help. How can you get a new algorithm, control algorithm in and make sure it works? Well, what he did is he said, well, let me give it control. Then I watch what it does to the car or whatever it's controlling. And if that gets into a state that I consider unsafe, then I'm assuming this guy misbehaved. I'm going to take control away from him and give it to somebody that I trust. And so this is then a way of bringing in here. It's a similar principle. Autonomy, let it be autonomous. If it doesn't work, we take control away from it or get it into a fail-safe state, which is, again, something that like NASA has been doing forever for their stuff that they send up into the sky.
So it's beyond redundancy, beyond graceful failure. Exactly. It is anticipating an alternative path.
And for those cases where you can't go into a fail-safe state that doesn't cause damage, and then go back and get feedback from an external entity, like contacting the ground or a car pulling over to the side and calling into somebody and say, hey, help me, give me a driver, since I don't know how to drive anymore.
So what are the challenges to...
I mean, that's when I watch Uber today. Yeah. I mean, they still have 2 guys sitting in there, but like if they wouldn't sit there and the car comes to some place, a scenario that it doesn't know how to do. I mean, what I would have programmed the car to do is pull over and call in and say, hey, I ran into something that I don't know how to do. Yeah, so instead of trying to drive through an intersection and cause an accident.
Yeah, like in Pittsburgh, when people take left turns at a time you wouldn't necessarily anticipate.
Yeah, that's the Pittsburgh Lift, for those of us that have been around long enough.
And so you want systems that can learn the Pittsburgh Lift and can react in a safe manner.
Sure.
So how does this work into a future lift? How's that for a pivot?
Well, interesting pivot. Yeah. Well, just to kind of make it a little more...
graceful pivot?
Graceful pivot, yeah. The ADL standard, like I said, was driven by the Army work. So we always did pilot and small projects to build up the know-how on how to do it and improve things. And then at some point, we got to a stage, first of all, the Europeans were much more systematic about it. So in 2004, the European Space Agency already had a 15 million euro project with 30 partners that used AADL. We were doing small projects with individual things.
They went big scale.
In 2007, the aerospace industry put together an initiative called System Architecture Vertical Integration. It was Boeing, Airbus, Embraer, and a bunch of guys. They then chose AADL as a key technology on that front. With our work with the Army, we got far enough, and then we had this nice situation that future vertical lift is coming up in 2020. Right now, they have this program called Joint Multi-Role. It's a technology demonstrator program. The idea is to test out some new technologies so that when they do the real product, they know whether it works or not. One part of it is on the aircraft itself, what kind of rotors to use and other things to make it faster. And then second piece is they knew that they won't get the software on anymore. Like in 2010, Dr. Lewis from Amberdeck down in Huntsville had contacted the SEI. At that time, he was the head of the Aviation Engineering Directorate. That's where they certify aircraft. Asked us to do a study about how to improve the qualification process, which resulted in this 4-pillar strategy that we have about virtual integration in the middle, requirements up front, verifying against whatever, that whole story. Given all of that, and then JMR came along, that's where they were then interested in trying out this, what in that context is called architecture virtual integration practice. The same concept as the other guys called Savvy. And so in the first round, they already had an ongoing project with 2 contractors trying out some technology, it's called FACE, to deal with portability. We came in the shadow. That is Steve Vestal at Adventium. And Steve Vestal is interesting because he's the guy that did the original meta-age work, which turned into ADL, us at the SEI. And what we did is we lived off the same documents, requirements documents, design documents as the other guys, captured that in an AADL model and in requirement specification and ran some analysis to identify potential problems, things they would run into later on. And so we identified a total of 85 type of things, some of them low-hanging fruit stuff, some of them relatively sophisticated things that, because of the semantics, we could put our fingers on. And since that thing then went well, the program office decided to accelerate bringing it into the program. So in the next BAA, they then already asked people to, not require them, but asked them to make use of some of this model-based architecture-centric type of work. So all 6 of those teams that were, the contracts were let this summer, are now doing work with this technology. And we're in the middle of going through mentoring, training, and maturing technology type of work, lots of interaction right now. So it has become a community effort to drive this forward.
So you have a very large base of people who have expertise in this already, and that's growing fairly rapidly.
We have that within the SEI. We have that outside. A number of universities are teaching it. Again, in Europe, they have been much more aggressive doing some of these things earlier, and here in the US, part of it there is because there is this systematic funding that's going on both at the national level and at the European level. And they always require research groups working together with industry. For example, even in places like China, they have a place where somebody from Europe gave a course and taught 400 people over there.
So we talked earlier about the early work that you did in your career and how the results of that work are really the underpinnings of what people take for granted when they learn about software engineering. It seems that this is the next wave that future college graduates will take for granted, that what we do is we model the architecture before we generate machine language that operates on the hardware.
Yeah, and so one of the things we had is 2 people that have been working with us at the SEI for quite a while. Dave Glutch, who originally was with the SEI, then went to Embry-Riddle Aeronautics University. So he taught the course there. John McGregor is doing that at Clemson University. In France, one of the guys that was involved in the standard is teaching at Aeronautics University down in Toulouse. And he actually runs students that aren't even in the software field through this thing.
Really?
That are electrical engineers, and they are using this technology and have no problem picking it up, which is kind of cool.
Yeah.
Because some people are saying ADL is too hard, or our fault modeling capability is too hard, and he just gives them the book and gives them a document and says, okay, here's a UAV, a little one, and here's, go do it. And they do it.
College students flying UAVs.
Yep.
Neat.
So people are, and this is what you find, is that a lot of people really want to do this stuff, know how to do it, and like in their head, and those that really understand their systems, you just need to give them the tools that let them express it in an efficient way, and then the analytical tools that drive it. And in other domains, we've had it. I mean, this is why on the CAD front, we have been able to, designing chips today.
It would seem to broaden their reach instead of laboring months and months writing the base code and then struggling through to make it work.
Yeah.
As we might have thought of it in the old days. You're really starting at a much higher, broader view of the system and specifying it.
Yeah, and one example of that is, like, again, since we're talking about safety critical systems, they have very good best practices in place. like there's this thing called ARPs, where you do a failure mode and effects analysis. And Myron Hecht, a guy from the Aerospace Corporation, one thing he said is, no, usually there's only 2 people ever read a FMEA report, and that's the 2 guys that write it. Because it's a spreadsheet type of thing that gets filled out.
I've written some.
And, well, given we can do that by annotating AADL, we actually auto-generate those things. He now, when he goes out and does satellite architectures, he now actually can do it as they do trade-off studies. Before, they only did it after all the architectural decisions were made. So this opens up new ways of looking at that whole space, and this is where we get into these trade space exploration type of activities. And it's on that front we actually got approved a LENS project for 1 year to look into trade space exploration using this technology.
So conquering new territories.
Yeah, doing some of that, pulling in work about trade space exploration that started out on the system engineering side. So they were doing it there. But the trade points that we have as part of the software system is a much richer set. And so what we're looking at is the statistical technique applicable in this context. And then on the other hand, can we take advantage of knowledge in the software architecture to reduce the trade space?
Okay.
Because like one concrete example is when you have your system that has multiple control systems, you tend to make sure that they all run at a very harmonized set of rates. So if you have 50 of those things, you don't have 50 points to trade. What you do is you do that in a coordinated manner.
Yeah.
And so if you make use of that knowledge, you can reduce your trade space, for example. So this is some of the stuff that we will be exploring in that LENS project.
So one of the things that comes with being named an SEI Fellow is a grant that you can choose which of the hundreds of things that interest you you can pursue. Which 20 of the 100 are you pursuing in the near future?
Well, that's a good question, and I thought about it hard, but I actually homed in on something quite interesting, and what it is how to deal with bias, uncertainty, like unknowns and falsehoods in data-driven decision-making. And the reason I kind of home in on that is actually quite interesting too, because when I look at in safety-critical systems, we make these criticality assignments, level A, B, C, D type of thing. In terms of reliability, we pick these numbers, and guess what? When you're level A, it's 10 to the minus 9. If it's B, it's 10 to the level 7. Why is it 9 and 7? Whatever, that you have that. In terms of assurance, you get into confidence, and if you talk to John Goodenough and Chuck Weinstock, they've been playing around forever coming up with a confidence measure. And what would be useful measures on that front. So there is that stuff there on one hand. And then on the other hand, I like to go to other domains and see how do they deal with that problem space.
Okay.
What's interesting is today we have big data, so some of that stuff is resurfacing. And there are some interesting publications that recently came out. One of them is by this woman called Cathy O'Neill. She has a book called Weapons of Mass Destruction. And what she means with that is people who are using data blindly, taking those measures. Automated algorithms make decisions that actually mess up your system rather than doing good with the system. There's another guy called Daniel Levitin who also just came out with a new book, Field Guide to Lies, Critical Thinking in the Information Age.
You have a very interesting reading list.
And he actually has also some interesting points, but I first actually ran across him because he wrote this book called This Is Your Brain on Music.
Oh, wow.
He's a neuroscientist.
Yeah.
But in addition to that, there's older work in operations research. There's a guy called Satie, actually over here at the business school at Pitt, who came up with this analytic hierarchical process.
Yep.
One of the elements that he has is because you're making value-based decisions, one of the nuggets that he have in his work is when people try to determine which thing is more valuable than others, you do pairwise comparisons.
Yes, analytic hierarchy process.
When you do that, how do you know when you do people are not always consistent?
Yeah. And he quantifies the level of inconsistency.
He quantifies, and guess what he does? He throws it in the matrix and calculates the eigenvector.
Yeah.
And that then tells you the consistency in that data. So what I'm interested in, how do they in different domains deal with the quality of the data, the degree of bias that you have?
Okay.
So for example, there has been some work in the area of behavioral economics where they actually have been able to quantify the bias that you have in your decision making if you only have partial access to the data set that is available to you. Like, for example, if I sell newspapers, if I don't sell out, I know how many more I could have sold. If I sell out, I don't.
That's a classic example.
And so actually my son's thesis was on coming up with a statistical quantification of by how much you're misestimating, and if you can do that, now you can compensate for that.
So somewhere in this, the Fibonacci sequence factors in. Have you found an application for that?
Not quite. But so my thought is to say, okay, there's a number of areas, like in control systems, they know how to get noise out of data, that kind of thing. Look for the nuggets from different domains and see if you can pull those together and then apply, and then go back to my domain and say, where can I apply those nuggets so that when we talk about confidence measures and those other things, can we determine when there is bias in there, when there is unknowns, how to compensate for the unknown, and those kinds of things.
A true Renaissance approach to solving a hard problem.
Exactly. Just step out of the box and do something different. I like doing stuff like that.
What a wonderful story.
Yeah. And again, that also is something that happened before to me when I was getting into the standards work. I was working with people on campus, and one of the people I worked with is Bruce Krogh, who is actually a hybrid like a well-known person in the hybrid control systems domain. That's why I can speak to that stuff nowadays too.
And that does seem to be a direction CMU is going more and more, obviously, integrating what has previously been thought to be disparate domains. And it's not just the bridge to the computer science building there. It's, there's an ID8 program. I have children thinking of going to Carnegie Mellon, so this is fresh on my mind.
Well, that's how my one son ended up in behavioral economics. He started up with Lowenstein over in decision sciences. And after the first year, he got involved in research on how emotions affect your decision making. For example, when you're sad, you value things differently than when you're happy. So if you see even just a 30-second clip of a sad movie scene, you will actually make economic decisions differently than you otherwise would.
So whereas we started our conversation on AADL and
now we are off
having
emotions.
certainty and being able to neatly bound things, we're now talking about very boundless areas.
Well, not necessarily boundless, because if I I just finished teaching the course on AADL, and those guys are flying home, and I gave them some examples about, for example, the auto brake system on the airplane not working. So they're now afraid to get onto the airplane. Clearly there are emotions involved. So if I'm now responsible of signing off a piece of paper that says this car shall be certified to be safe, it's not just numbers anymore. You have to take emotions into account. And this is why I think this whole field of, say, decision science or behavioral economics is so fascinating, even to me, because of that interplay.
It's easy to see why you are an SEI fellow. If you could imagine 5 years from now where this trajectory of work will take us, if we pick that arbitrary point in the future, what would you forecast?
Well, it's actually something we had touched on earlier, this whole notion, at least in the context of safety critical systems that also have security requirements, is the whole notion of robustness and resilience. That is critical, and you can't do it with just pure firewalling. You need to have you need to do isolation to scope it down, and you need to have some external reference models, continuous monitoring that then makes sure that what your expected system behavior is meets up to what it actually does. Whether that's now because of intrusion or that's because of some mistakes in software doesn't make a difference. A lot of the pieces are in place, but I think there can be some additional things that can be done that also require interaction on the hardware side. And actually one of the reasons I'm saying that, it goes back to my history part. When I was at Carnegie Mellon, we were doing capability-based systems, and all the two multiprocessor systems actually had hardware support for access control and everything. The Intel then did a process called the 432 that had hardware support for it. That one didn't work so well, which caused them to do this project with Siemens that I was out there for. And some of those ideas showed up in the i960. It was just 30 years too early.
So
technology that we need today is what we had at that time already, is, for example, an example of where we can make some progress in this area that we struggle with a little bit.
So a richer set, a more complete set of reference models to guide.
And in that context, also continuous enforcement at all levels, not just at the outer bound. And that's what gets to the robustness part, and then the resilience part is the ability to understand what do you expect in the world so you can adapt to it, and if you don't understand anymore, have a fallback position, like we had talked about earlier.
Well, I hardly know how to stop this great conversation. Thank you very much for joining us today. This has been very interesting.
Anytime.
This podcast is available on the SEI's website, as well as on Carnegie Mellon University's iTunes U site. As always, please don't hesitate to reach out with any questions. Thank you.